with 17.4 is just a lot of good practice on molar solubility. So use the KSP values found in table 17.2 to find the molar solubilities of the following compounds. Let's see, can we fit them all? Just barely. I won't do that. There we go. Okay, so for manganese sulfide, we know that this has just one cation and one anion, so the KSP is going to equal x squared, and so x is going to equal the square root of the KSP. All right, we can get that from an ICE table, but it's so simple. Just go back and look at the lecture again to understand how we get these relationships. I'll go into a little more detail for the more complex ones. But that means that's going to equal the square root. The KSP value for the manganese 2 sulfide is 4.6 times 10 to the negative 14th. And so the molar solubility is going to be 2.14 times 10 to the negative 7th. And that's a molar quantity. So let's look at now the magnesium hydroxide, MgOH2. So for this one, the KSP is going to equal the magnesium concentration. That'll be an X. And then the hydroxide concentration is a 2X, and that will need to be squared. Because there are two hydroxides, that 2 will come up here as the 2X, and it will come up here having to be squared in the equilibrium expression. And so that means that KSP is going to ultimately equal 4x cubed. And so x is equal to the cube root of KSP over 4. And I'll express the cube root in that way. And the KSP for magnesium hydroxide is 5.61 times 10 to the negative 12th. Multiply that by 4, cube root it, and you get 1.12 times 10 to the negative 4th molar. And now we'll scroll down to the barium 2 phosphate, barium phosphate. So Ba3 PO4 2. This is going to give us an equilibrium expression where the KSP is going to equal the barium concentration. Because of that 3, that will be a 3x. And then that will need to be cubed. And then the phosphate concentration will be a 2x. And that will need to be squared. And this ultimately will give us 27x cubed times 4x squared. That's 108x to the 5th. Now this looks kind of awful, but ultimately we can say that x is equal to the KSP divided by 108 and take the 5th root of that. It's not so bad, really. The KSP for the barium phosphate is 3.40 times 10 to the negative 23rd. We'll divide that by 108 and take a 5th root, and that'll equal a molar solubility of 1.26 times 10 to the negative 5th molar. So hopefully you can see these are pretty reasonable as far as the math. We're not having to solve quadratic equations or anything. We just need to remember that the coefficients in the balanced chemical equation, which come from the subscripts in the chemical formula, are going to show up in both these places, and we need to sort of make sure that we handle those coefficients properly. Okay, let me erase all this. We'll scroll down to question 2. So use the given molar solubilities to find the KSP for these following ionic compounds. And you could cheat and look at table 17.2, but let's not do that. Let's use the molar solubilities that we're given. So for calcium sulfate, we're going to use the exact same sorts of expressions. The KSP in this case is going to be just x squared. And x is the molar solubility that we're given. So 7.02 times 10 to the negative third squared. And that gives us a KSP of 4.93 times 10 to the negative fifth. 4.93 times 10 to the negative fifth. Let's look at the lead iodide, PbI2. KSP is going to equal the lead concentration times the iodide concentration. That is 4x cubed. Hopefully this is beginning to look familiar to you. And so we'll take 4 and we'll cube that molar solubility. 1.35 times 10 to the negative third, and we'll cube it. And this is going to give us 9.84 times 10 to the negative ninth. And then our last one is the aluminum hydroxide. The KSP here is going to equal the aluminum concentration times the hydroxide concentration cubed. And so this is going to simplify to 27x to the fourth. And so we'll take 27 times that molar solubility, 3.61 times 10 to the negative ninth, and raise that to the fourth power. And what we end up with is KSP of 4.59 times 10 to the negative 33rd power. And you may notice these molar solubilities are pretty similar. This one's only off by a factor of 10 to the 6th, but their KSPs show a much wider variability. For example, this is a factor of 10 to the 4th power, and this is a factor of 10 to the, like the 20th or so power. And that's because your molar solubilities, well, they get squared or they get cubed or raised to the 4th power, and raising them to different powers really sort of exaggerates or accentuates their differences. Okay, let's move on to question 3. Now this is one of my very favorite questions. It's not particularly difficult, I just think it's a really cool question. So we have the tin 4 sulfide. This is a compound with a remarkably small KSP value of 1 times 10 to the negative 70th. And so we want to calculate the volume of water that is required to dissolve just 10 formula units of tin 4 sulfide. How much water do I need to have just 10 tin ions in solution? So we can find the molar solubility with the expression that the KSP is going to equal x, the tin concentration, and then 2x, the sulfide concentration squared. So that's going to equal 4x to the cubed. And so x is going to equal the cube root of our KSP, which is 1 times 10 to the negative 70th, divided by 4. And what do we get? 2.92 times 10 to the negative 24th molar. And that's moles per liter. Well, how can we proceed from here? This molar solubility is a number of moles per liter of volume. It can be thought of as a conversion factor between moles and liters, or liters and moles. So what we'll do is we'll start with 10 formula units. That stands for formula units. And do dimensional analysis from there. So I want to get into moles. I know that it takes 6.022 times 10 to the 23rd formula units to get 1 mole. And I know that 2.92 times 10 to the negative 24th moles is going to give me 1 liter. So that's all there is to it, a pretty simple dimensional analysis problem, and you end up with 5.7 liters. So this salt is so insoluble that 5 liters, which is, you know, a pretty good sized little bucket or something, is only going to have 10 formula units in solution at any given time. And kudos to the analytical chemist that measured that KSP, that had an instrument sensitive enough to detect the presence of tin ions in such low concentration. Okay, last one. This one's going to explore the common ion effect. So cadmium fluoride has a relatively high solubility. It's not like sodium chloride, truly soluble salts, but it's a decent little champion there among the insoluble salts. So we know that KSP is going to equal the cadmium concentration times the fluoride concentration. We're going to find its molar solubility first in water. Okay. That's going to equal 4x cubed. Boy, we've seen this 100 times before. X is going to equal the cubed root of its KSP, 6.44 times 10 to the negative 3rd divided by 4. And so its solubility in water is 0.117 molar. Not too bad. What about its solubility in a 0.5 molar solution of sodium fluoride? Now in this case, let's write the actual equilibrium expression. 2F minus, we'll do an ice table. In this case, we don't care about the cadmium fluoride solid. We'll start with a 0 amount of cadmium, but we have 0.5 moles of fluoride in solution already, because it's a 0.5 molar sodium fluoride solution that we're trying to dissolve this into. Well, the change is still going to be plus x and plus 2x, and so we get x and 0.5 plus 2x. Well, that means that our KSP, our equilibrium expression here, is going to be a little bit different. We'll have 6.44 times 10 to the negative 3rd is equal to x times 0.5 plus 2x. And this needs to be squared. There we are. Now, it would be nice if this x were small. Then this would simplify to 6.44 times 10 to the negative 3rd is equal to 0.5x. And we would get a value of x equal to 0.0258. However, what we need is 2 times x to be small relative to 0.5. So if I get 2x divided by 0.5 times 100%, what this gives me is like 10.32%. That all just barely stayed on camera. Okay, 10.32% is too big of an error. You know, this value of x is probably not very accurate. So we need to go back to solving the actual equation. Now you might think, okay, quadratic formula, it's a pain, but I know how to do it. This is actually not a quadratic equation. If we were to FOIL this out, then we would get a quadratic equation here, and then it is multiplied by x. That makes it a cubic equation. Now go ahead and Google the cubic formula, and you're not going to find one. If you discover a formula like the quadratic formula that works for cubic functions, then you'll be the greatest mathematician of our age and probably win million-dollar prizes. So good luck with that. In the end, we're going to have to rely on numerical approximations. And by that, I just mean let's go to Wolfram Alpha. Okay, so we've got 6.44 times 10 to the negative third, and that is going to equal x times 0.5 minus 2x. And I'll just let Wolfram do the work for me. You could also solve this graphically on your calculator by making one function equal to the left side, 6.44 times 10 to the negative third, another function equal to the right side, x times 0.5 minus 2x. Anyway, we'll come down here and find the solution. The value down here, 0.236, that actually does not make sense because, oh, hold up. Well, that might be a valid second solution, huh? That's a little funny. Give me a minute here to think about that. Is there anything wrong with that? Well, anyway, the solution that I was interested in was the 0.0136. 0.0136, you'll notice it's about half of the value of x that we had calculated. That's going to be our valid answer here. Oh, that's why. Hey, I'm so sorry. Okay, can we pause and come back? I'm just, at force of habit, with acid-base problems, I put a minus 2x. It should be a plus 2x. And that's why none of these numbers quite worked out the way I was expecting. Okay, there should only be one valid solution. You'll get a negative root, but x can't be negative in this case. We can't dissolve to a negative molar solubility. That doesn't make any sense. That's interesting. Oh my gosh, I'm the worst. I forgot to square it. I'm so sorry. It's a good thing I did this ahead of time and I have the solution, and I keep noticing that the answers I'm getting are different than the solution. I apologize. That needs to be squared. 0.5 plus 2x needs to be squared. And now finally, we should come down here and get a solution that makes sense to me, right? X is equal to 0.0218. Now, that's less than the x that we calculated with our assumptions, and we see that that assumption was indeed a poor assumption. We should really use x equal to 0.0218. And so we'll cross that out. We'll say we let the computer do it for us, and the computer says it's 0.0218. Let me erase all of this because we're running out of board space. 0.0218 molar. Now we can compare that to the solubility in pure water and see that it's maybe about 20% of that value. And so the solubility in the sodium fluoride solution is only 20% what the solubility is in pure water. And that is the common ion effect.